Okay, so I'm John Swain from Right Relevance, and I'd just like to take you back to October the 2nd. We published our first analysis of the data that we collected on the Twitter conversation around the election. This was actually, it took us a while to get going. This was the data from September the 11th. And if you remember on that day, the big stories were Hillary's collapse and her comment about a basket of deplorables, I believe it was. All the talk on that day was about Hillary potentially having to resign, so things changed quite a bit. It's a very crowded conversation, intensely covered by the media, obviously. And what we just wanted to demonstrate was that behind all the noise and the obvious stories, there were some things that you could see in this data that were maybe not quite so obvious. So we did some analysis, and we identified this cluster of people. This is a Gephi map of about 15,000 of the users from that day, the top users. And one of the clusters that we identified was a bunch of journalists, the most prominent of whom was this guy, David Fahrenthold. So that's what we said on that day. Fast forward to October the 7th, which was last Friday, this story broke. And it was this guy that broke the story, if you remember. So I'm just going to today tell you how we went about discovering that group of people. Obviously, there's a little bit of luck involved in such a big story breaking a week before this, but hopefully show you that it wasn't a fluke. It's the kind of thing that's repeatable. So very briefly, just split into three parts. The problem we set out to solve, the data that we needed to solve that problem. Processing the graph data with Neo4j and R, which was where we do all our analysis. And then how Neo4j and specifically Ryan and Michael, if he's here, helped us to scale that when we hit some scalability problems. So a little bit of background. This project started for me just about 2 years ago with the Ebola crisis. It was a volunteer project for the United Nations. And we were looking for information like this in the Twitter conversation about Ebola, and to identify people who were putting out information that was useful in a variety of different ways. The nature of the project, there was no budget, it was a volunteer project for Statistics Without Borders, meant that we had to use, or I had to use, open source software. There was no budget for expensive systems for doing this kind of analysis. So started life with R, the Neo4j Community Edition. Very quickly ran into a problem, which was, if you remember, there was one single case of Ebola that hit the United States in Dallas, a guy called Duncan, I believe, and it coincided with the midterm elections. And what happened was the whole Twitter conversation about Ebola got hijacked by this organization called TCOT that I'd never heard of before, and some other sort of politically right-wing people suggesting even things like that President Obama was responsible for the whole thing, that you could catch Ebola in all kinds of weird and wonderful ways. And it completely crowded out the whole conversation. And we had to come up with a solution to that problem, which we did, or I did. When I'd done that, I realized that actually that we could generalize that solution and help us in other situations where we're trying to gain insight into situations that are confusing, strange, or new. That pretty much describes the current election situation at the moment. So where did we start? Well, started with something that everybody's pretty familiar with, the common internet trope about the law of the few. We started with Stanley Milgram's famous experiment, identified that we're all connected by 6 degrees of separation, spawned things like the Kevin Bacon index, and popularized by the Malcolm Gladwell book, The Tipping Point. In there he says that any social epidemic is dependent on people with a particular and rare set of social gifts to spread information through networks. So whether you're trying to push your message into a social network or whether you're listening to messages coming out, the mechanism's the same. It's special people that have these gifts that can do that. So the plan was to collect the Twitter data, map these relationships, and then do some analysis on how the mechanism for the information was being spread. Then we could separate out the noise from the message. So data we needed to achieve that, it's fairly straightforward. So I thought, start collecting data from the Twitter API, and we'll build this data model in Neo4j. This is currently available as a stand outside, actually, I think, is that right, Ryan, at the moment?
We're happy to demo it to you.
Right, we can demo this. And so you can sign up here, put your own Twitter sign in, and it will generate a graph, and you can run Cypher queries against your own graph using this graph model. The original source code is also still available on Nicole's GitHub, so the Python scripts and the import routines for pulling this into Neo4j. However, for our purposes, there's a problem. That at the scale we wanted to do it, you can't collect the followers and following information. The rate limits on Twitter API are too limiting. You cannot get enough of that data. So we kind of hit a full stop. How are we going to do this? So it's kind of back to the drawing board and a bit more research. And actually came across there's two very good books now by Duncan Watts, but he was one of the first people to do some empirical research on this law of the few, 6 degrees of separation. And the empirical research shows that actually there's a problem with it, and that is that it doesn't work like that. That actually, and the way he put it is, again, this is thinking about pushing messages into a network, but any process that relies on targeting a few special individuals is bound to be unreliable. No matter how popular and how compelling the story, it simply doesn't work that way. So actually, we kind of rechristened it the law of quite a few. And we named the people that actually are responsible for spreading information through social networks ordinary influencers. So these aren't just anybody, they're people with some skills, but it's not the special individual. The kind of money that people spend on getting Kim Kardashian to tweet about their products is generally completely a waste. It's grossly overpriced for the value that it delivers. We also came up with a methodology. It was we by this point. I've got a colleague who's actually my brother-in-law, who's a commander in the British Navy, works in military intelligence, and we borrowed this methodology from military intelligence called the OODA loop. This is a simplified version. It isn't much more complicated than this, but there's a little bit of noise in the full version, which we adapted for social media. Basically, OODA, observe, orient, decide, and act. And the key thing that we learned in the research before we started this was that people tend not to be too disciplined about this. So the process is we collect the data, we do initial observations, started by some implicit guidance, which is your initial idea of what you think is going to go on, and don't overanalyze that, make a start. Do the orientation, make some decisions, and feedback. But importantly, feedback right to the beginning and start your observations again. What tends to happen in practice is people don't do that. We don't do that. We're all guilty of this. We do some initial observations, we orient ourselves, we understand what's going on, we start taking some actions, but we shortcut the feedback loop. So what we think we know the situation is, and we're not disciplined about going right back to the beginning and re-looking at the incoming data. So if you're using a feedback loop like this is basically hindsight bias, which means a hindsight bias is the belief that if you'd looked hard enough at the information that you had, the events that subsequently happened would have been predictable. So often we say with the benefit of hindsight, meaning if I'd known this with the benefit of hindsight, we could see how it happened. And it gets kind of perverted to mean, actually, I could have known if I'd looked at that a little bit harder. And that's usually not true. It's the information you didn't have at the time. These events aren't predictable. They seem predictable playing the world backwards, but they're not at the time. They're not predictable. So that was our methodology, and we decided we were committed to Neo4j at this point. We're going to build the graph. This is the graph model that I showed earlier. I just could briefly talk about ingesting into Neo4j, building the simplified graph model that we need to do the analysis on the conversation, and then the processing with R and iGraph. So the first part of the process is the ingest into Neo4j. Data gets collected from the Twitter API, comes in JSON. We actually scale this up, so we've got we push this. We use the raw API rather than the Twitter API libraries in Python. Push that into a message queue and store this in a document store, MongoDB. Whether you're pulling this from the raw API or whether you're pulling it from a document store, you get a JSON document. And when we did it, this was the way to do it. We push a Python list into this Cypher query and use the unwind command. And I did have down here a reference to an article about how to do that. It's very interesting, but Ryan tells me now the preferred method is to use the APOC load JSON library. So this is a slightly better way to do it. This is the way that we still do it. And what we're interested in is a simplified version of the graph, which is these relationships here. I'm not sure how well you can read that. But basically, we're interested in users who post tweets that mention or retweet other users. And we separate into those two. At the moment, we build the graph in those two ways, retweets and mentions. The data that comes from the Twitter API for mentions includes retweets. It also includes replies, any form of mention. Retweets is just retweets. So we build the simplified graph, which just is the relationship between each user with a weight for every time that happens. And this is an R call, procedure call, very similar to the Python one, calls a query string, which is a Cypher query. Cypher query just says match users who post tweets that mention other users with some conditions about the time period, that they're not the same user, etc. But basically, that's how Cypher works. Builds a simple edge list for each pair of users, the number of times in each direction that they're mentioned or retweeted. In this case, it's mentions. And we get a graph. And we want to make sense of that graph. So we're going to run some graph algorithms. This is a Gephi map of the kind of raw graph. Doesn't tell you very much. That's the starting point. The key point at this stage is that we have no external training data to do things like sentiment analysis for two reasons. One, it's a cold start problem. Often we're looking at a brand new situation. We don't have any information. And the other is that social phenomena like this are inherently unknowable. No one could have predicted that this story was going to break. No one could have predicted that this guy was going to be an internet sensation this week. It's inherently unknowable. So at this point, we need to use unsupervised learning algorithms to make sense of the graph that we've created. First one that we use, very well known, algorithm PageRank, originally adapted from an eigenvector centrality algorithm by Larry Page to index web pages, and basically ranks web pages or any other node in a graph according to how important it is in relation to all the pages, the importance of the pages that link to it recursively. And this is an example of what we can see just using a simple PageRank. So this is the same graph that we started with at the beginning, with the top PageRanked users. I don't know how well you can see it. I think you can actually, but there's a little like spark lines here which show that one of the issues with PageRank is it's very heavily skewed. So in the top 3 users in this was the first. Actually, no, this is a different data set. This is the first debate. And the 3 users, Hillary Clinton, Joe Biden, and Donald Trump, heavily skewed the PageRank. There were a couple of other interesting users that we could see from this, including Jerry Springer, who had an enormous number of retweets. That's a big number of retweets. Even Kim Kardashian doesn't get that very often. And, you know, it's a funny line, right? It just kind of illustrates this temptation to think about special people. Looking backwards, it's very easy to put together a plausible reason why Jerry Springer was so successful. He had some special insight because of the people that he has on his show or something. Reality is, it was just luck. It could have been one of 10,000, I don't know, there's A-list, B-list, C-list celebrity these days, but it's just one of those things that happened. But it's tempting to look back and rationalize what happened and believe that you could have predicted it and say to yourself, right, we missed it this time. We only picked this up after it happened. But he's a special person. If we study why he's a special person, we can find more of those special people. And that's the myth. Next algorithm we use is betweenness centrality, which measures for each user the number of shortest paths from all the other users that pass through that user. Tends to identify brokers of information in a network. Information is passing through those nodes. So like an airport as hub, all the traffic's going through those users. Oops. We also collect and measure some basic stats, some of which are collected out of the graph that we've created. In degree, total number of inbound links, out degree as well, which is outbound links. And counts of retweets, replies, and mentions within this graph. So in the case of something like the election, the debate, it was 24 hours from just before the start of the debate to 24 hours later. From the API, Twitter API, we also get information about the user, total number of followers and following, even though we don't get those individual relationships, the total number of tweets that user's ever sent, and the number of times that user's been listed. There's a few other things as well, but this kind of information we collect. And then what we create is a set of derivatives which answer some natural questions. And an example of that is a metric that we call talked about. And the natural question is, who's talked about? This is the same night, the first debate. And the talked about measures, it's a ratio of the number of times someone's retweeted to the number of times that they're mentioned, corrected for number of followers, and a couple of other things as well. Obviously, if Katy Perry is always mentioned more than anyone else, simply because she's got 80 million followers on any topic. So we adjust for that. And it measures the level of importance of a person in this graph from influencers outside their participation, which can be someone who's not very active on Twitter, someone who just isn't involved in the conversation at that time. In the Brexit dialogue on Twitter, Don't know how many have heard of Boris Johnson. He's now our Foreign Secretary after the vote. He's not very active on Twitter. He's a very big player in the conversation, so he tended to get picked up by this metric. He wasn't involved in the conversation, but people were talking about him. On this night, the most talked about person was Lester Holt. He was obviously busy that night, moderating the debate, wasn't tweeting a lot, but people were talking about him. And we consolidate all the measures together into an overall measure that we call rank, which combines these and some other metrics. PageRank between this measure we call interestingness, which is the difference between how someone's PageRank, what someone's PageRank is, and what you'd expect their PageRank to be, given a regression on various factors like reach, number of followers, and reach. So obviously, someone who has a very successful meme that's retweeted a lot, gets a lot of mentions, can be influential in the network. So, but we try to correct for that just being noise versus actually being valuable information. And this is the same graph that we saw earlier. And obviously, it's natural that these two people are going to be always the top influencers in any network on this, any graph on this subject. But we collect, it evens out a lot of those distortions and skews from some of the other metrics, and gives you a good idea of who is genuinely important. We're talking about influence. It's not something you can directly measure. It's not something you can directly compare. There's not necessarily any perfect right or wrong answer, but you'll get a good indication on any given time period who's been important, influential in that conversation. So the next thing we do, you probably notice the colours on the maps, is community detection. Community detection separates groups of people by the connections between them. And in this toy example, it's easy to see that there's 3 distinct communities of people. In reality, we're all in lots of these communities at the same time. So, we might have a political affiliation, follow a sports team, chat with the guys down the local bar. We're doing this all the time in a very sophisticated way. However, the algorithms that calculate that kind of non-overlapping membership of communities are very computationally intensive. So the solution that we came up with to that, we run a couple of algorithms on multiple subgraphs. So we take subgraphs based on in degree on different types of giant component, which is a centrally connected, most centrally connected part of the graph, and run those several times, and then ensemble the results together to create this multiple membership. And it looks something like this when you visualize it. This is back to the UK Brexit conversation. About 2 million tweets in this particular example. There's 2 things to notice. One is, I said earlier that we create 2 types of graphs, one based on retweets, one based on mentions. The retweets graph always creates this clear separation of communities. No matter what people say on their Twitter profiles, retweets do mean endorsement on aggregate. People congregate very clearly in groups where they share common beliefs. Mentions and including retweets gives you a very different structure. Not quite so clear. It's not great, but you can see there are 2 communities, but there's a lot more interaction between them. It's not quite so clear. And the same with the community detection algorithms. The 2 that we use most of the time, WalkTrap and InfoMap. WalkTrap tends to create fewer, larger communities. When you combine that with retweets in this way, you get very clear separation. There is actually a third up there, but you can't really see it. Whereas the InfoMap algorithm creates lots of much smaller communities. So if you think about this kind of situation, say there's a main, in this case, it wasn't a political affiliation, it was the vote to leave the EU or to remain, very clear separation. At the same time, people had existing political affiliations that overlap with that, and there's lots of small communities. It's not usually so easy to see on the kind of 2D visualization with colour, but you get some idea of what's going on. So yeah, at this point we get some sense of what's going on in this conversation. Go back to debate 1. This was the community. This was the community that we detected for Joe Biden. And these kind of communities we call flocks. These are the people that are active in that conversation at that period in time. And this is totally unsupervised learning. There's no supervised learning, and there's no human input into this. And you can see that, by and large, pretty accurately, it's a coherent, sensible community of people sharing certain political affiliations. So we were happily going along, doing this kind of analysis and getting bigger and bigger graphs. And then during the Brexit campaign, the last week, created this huge volume of tweets. And we hit a brick wall with scalability. And we realized, we knew this was going to come at some point. But I think something like 20 million tweets that week, we knew that we couldn't handle the capacity. We needed to scale the graph algorithms. We looked at various options, including GraphX on Spark, but we decided, after talking to Ryan and Michael, that we could do this natively in Neo4j using APOC. And our target, we're currently processing about 20 million after some of the help they've given us, but our target is to reach capacity to do a billion node capacity. And Ryan's going to tell you a little bit about APOC.
Sure. Maybe. Microphone? Hello? Can someone turn on the mic? Hello? Okay. Maybe I'm going to tell you about APOC without the microphone. Do we know the mic person? Hello?
There you go.
Oh, it is on. Okay, so my name is Ryan Boyd. I'm on the developer relations team here at Neo. And I just wanted to give you a little bit of an overview of user-defined procedures. How many of you have used user-defined procedures? Okay, I'd say 10% or so. Well, user-defined procedures basically is just that. It's the ability to write code that executes on the Neo4j server alongside your data. To increase performance of any sort of analytics process, you can either bring the processing to the data or the data to the processing. And in this case, we're moving the processing to the data. So you have your Java stored procedure that runs in the database. Neo4j can call that through Cypher, and then your applications obviously can issue Cypher requests. At the bottom here, you see an example call. As a procedure, basically they yield results. So the first thing is using the APOC feature to create a UUID, and the second thing is using APOC to create a timestamp of the current time. And then the third thing, we're saying create a node and include that UUID and the timestamp that was yielded from those two procedures. So you can do that all in that one Cypher statement, but in 3.1, we have user-defined functions, which make it even nicer. So user-defined functions allow you to call these as functions rather than procedures. So if you look at the bottom, right in line with your creating of your document node here, you can call the ID, set the ID property to be apoc.create.uuid, and then set the created property to be apoc.date.format and your timestamp. So it just makes it a lot easier to call directly. We've taken a lot of the functions the procedures in the APOC library and converted them to functions when that makes sense. So the next version of APOC is out there for testing, the 3.1 version. But APOC is basically a library that is contributed by the community and by some Neo4j folks. It's an open source library. It has all sorts of different functionality in it to call JDBC databases, to integrate with Cassandra or Elasticsearch, some ways to call HTTP APIs and integrate pulling data in from web APIs like Twitter or what have you. But it also has things like graph algorithms. So John's going to go a little bit more on their work with graph algorithms that they have written as a company and contributed to the open source APOC library, and now all of you folks can use them.
Okay, thank you. Yeah, so basically, we've started work on creating the graph algorithms that we're going to need to migrate everything from running the algorithms in iGraph in R to running it natively in Neo4j. So we started with PageRank, Betweener Centrality, and we're currently working on these two community detection algorithms, WalkTrap and Infomap. Everything's available, it's all open source on GitHub. It's a community effort. We see these algorithms as basic building blocks that lots of people are going to need to do this kind of analysis, and we're hoping that people will contribute and join us and help develop more of these. It's actually the tip of the iceberg. It's quite a long way for us to go till we complete the process so we can run this end to end. And so we've got some initial results. We've run on 3 test graphs. This was from Brexit data, actually, 2 days worth of data where we'd got total number of tweets of 800,000, 1.7 million and 3.9 million, with these total number of nodes and relationships in that simplified graph that I described. And PageRank, actually, the iGraph implementation of PageRank's pretty efficient, so we're only getting like a 2-fold in performance improvement. But with Betweener Centrality, we're starting to get much bigger performance improvements. That's pretty intensive algorithm. But critically, because we can run it natively in Neo4j, we don't have to build that graph projection and then move that graph into iGraph. So we get a big win when we build that graph. Doing that in R, on fairly small graphs, we get a huge improvement here. That's much more efficient. At a certain point, we just run out of capacity, run out of memory, it starts paging, and performance on our current system really goes flat, and we get a big improvement doing it this way. So just to wrap up, how we put all this together and go back to where we started and how we discovered what we discovered. So we talked briefly about the special people versus ordinary influencers, and the fact that when I started, we didn't have that information about relationships and what we could get from that kind of. Actually, with the right relevance system, we do have that information. We have approximately 2.5 million users on 50,000 different topics, and we give everyone a score of their topical influence in all those topics. So this is the guy we started with, and you can see he's got some significant influence in lots of related topics, and some of which were in that conversation that we looked at right at the beginning. So what we're trying to do is find the intersection of 3 things. The conversation, which is what I've talked about, how we analyse that. Trending topics, so what the topics are being discussed in that conversation. That's kind of defined by the initial search that we do, but also that can be quite difficult defining the track phrases they're called for pulling data from the Twitter API. So you can get multiple conversations and you're not quite sure what the topics are going to be. And then this kind of influence, which we call tribes. So the difference between flocks and tribes is people who are in groups of which we call tribes tends to reflects their intrinsic values, their demographic or psychographic qualities. So football team's a perfect example. People who support a certain football team, that's a classic example of a tribe. It changes very slowly, if at all, but it's not necessarily active. If I support Manchester United, I might not be doing anything about that quality today. But if I'm going to a game, and there's a particular piece of news about a player that's being signed or whatever, then I'm engaged in a conversation. The people who are involved in that are in flocks. So what we want to find is the intersection of these three things. So just to go right back to the beginning, I appreciate this is quite a busy slide. These are those, in this conversation, which was September the 11th, these were the topics. It's a slightly long list that's truncated for the topical influences. So the people in this conversation had expertise or influence in these topics. That's just a filter. This is a Tableau dashboard, actually, which selects the people in that flock. So this is now the intersection between people with this topical influence and the people in this flock. So people who are active and reporters and journalists, which gave us this list of people. So that's how we did what we did, right back to the beginning. One final thing, which is, that's where you've got to be really careful with reviewing and going back to the observation phase. This is a later analysis, and what we've detected is something that's happening slowly but detectably, and expect the next analysis we do for the next debate, which we expect to get out within 24 hours of the debate happening, that this process will accelerate, that what's happened as a result of the news in the last week or so, basically establishment commentators, established media, the metropolitan elite, whatever you want to call them, has gradually become more and more prevalent in this side of the graph, which is the Hillary Clinton side of the graph, leaving this Trump side quite sparse in terms of the number of influences. You can't read all these. And we're not making any judgment about whether their influence is in some kind of worthy or important topic. It could be anything. It could be TCOT, it could be something very partisan. It's just anyone who's got any influence at all in one of the topics that we measure. We're not trying to make a judgment and say, oh, these are, the people that are making quality judgment, journalists, etc. But this side's getting very sparse. So what's potentially happening here is everyone in this side of the network is starting to listen more and more to those people. And it becomes this a filter bubble, self-reinforcing, stops looking out, starts to believe what they're hearing. And it's very similar to what we detected on Brexit. There's some significant differences. It's the other way around. So in terms of for Brexit, this was the Leave side, and this was the Remain side. So Remain was very much establishment, the status quo, obviously. So people were not so active. In the election here, you've got two very active sides, so that's one difference. But what the similarity is very stark. This is also all the group of influencers in the Brexit campaign in the UK. Anybody who was anybody really was supporting Brexit, supporting Remain. No one really believed, including, if you believe the reports in the newspaper, the main proponents of Brexit didn't really believe it was going to happen. But it did. There was a complacency. People just, the turnout was very low on this side. So, that's potential that could happen in this election. I know it's been in the news the last few days, big publicity on Facebook, etc., to get people to register to vote. So, that's it from me. This is the Graph Connect graph on Twitter as of today. I did that a couple of hours ago. So I don't know if you can see yourselves on there. But we'll take some questions now. And then after that, I'm going to be at the Graph Clinic for a while if anyone's got any further questions.
Thank you very much, John and Ryan. So I think we are ahead of time, so we can take one or two questions.
Okay, cool.
So, yeah, let's start with that.
I'm not sure this is relevant, but do bots play a factor in that? I mean, you can't, I don't know if there's a way to identify what is a bot, but
yeah, absolutely. Yeah, I mean, go back to that one of the first slides, those big purple swirls. In actual fact, most of those were bots. filtering those out can be relatively simple in some cases, but there's some quite sophisticated ones that are much harder to do. But it's generally polluting the conversation with a lot of noise. Sometimes the UN actually wanted to track that because a lot of that noise was potentially very damaging. People saying how you could and couldn't contract Ebola, what the cures were. They really, some of that was potentially very damaging to their efforts. So, but in most cases, you just want to ignore it.
Over here.
I just wanted to know, how did you validate the accuracy of your outcome? How did you validate the accuracy of your outcome?
How do we validate the accuracy of the outcome? That's a very good question. A lot of this is, as I said before, is inherently unknowable. There's no training data. It's not necessarily a situation where we're looking for that kind of validation. We're not looking for accurate predictions about what's going to happen. So we weren't looking to predict what was going to happen with Brexit. One of the questions that we were asked subsequently by hedge funds, for example, was, could you have predicted this? Everyone else didn't. Could you have predicted it? And the answer was, no, we definitely wouldn't claim that. What we could predict was, it was a lot closer than people thought. So in that kind of situation, it's not necessarily looking to predict very precise things which can be validated. Again, this comes from the sort of military doctrine and techniques that we use. You might just be looking for an edge, an advantage, something that you know where to look, you know who to observe, rather than exactly what's going to happen.
But we also are, as we're moving the algorithms to APOC, or as John and his team are moving it, we're validating the results of those algorithms versus the R and iGraph implementations to make sure that they're returning the same result on very large data sets. So that is an area where we can at least say we have 2 implementations done by different people returning the same results.
Yeah, sorry, if that's what your question was about. Yeah, we can validate that the algorithms are returning exactly the same results. That doesn't necessarily validate what that means. Yeah.
Okay, thank you very much, John and Ryan. As I said, please find them at the Graph Clinics just outside if you have further questions. Thank you very much.